This video is going to show you how to do problem number 17 in chapter 10. So let me read the problem to you. A recent poll of 809 randomly selected registered voters, so we have an N of 809, revealed that 426 plan to vote for your candidate in the upcoming election. So you can think about this as really an XB. If you want a symbol for it, we've been calling this XB in the past. So 426. It's like we flipped a coin 809 times. We've observed 426 heads. Now from this, you might want to compute the sample percentage, which is 426 divided by 809. And that works out to be about 0.5266. So about 53% of the sample indicates that they're going to vote for our candidate. The question is whether the observed percentage is more than 50%, and the answer is yes. So the observed percentage is greater than 50%. So that's the answer to part A. Part B says, is the observed percentage significantly more than 50%? How do you know? Base your answer on a two-sided test. So I don't quite like his language there because he's kind of leading you to a one-sided test, then he tells you to do a two-sided test. But let's do what he says. So let pi equal the true percent in favor of our candidate. The null hypothesis is that pi equals 0.5. So we're asked to test whether it's significantly more than 50%. So pi is equal to 50% or 0.5. We're explicitly told to do a two-sided test. So pi not equal to 0.5 is the alternative. So let's go draw what we have here. This is the sampling distribution of the percent. And it's going to be roughly normal. How do I know that? Well, n times p is greater than 5, n times 1 minus p is greater than 5. The normal approximation ought to be plenty good. When we do a hypothesis test, we always start by assuming the null hypothesis is true. We're going to condition on the null and then evaluate the evidence against it. So that's super important to get that. Now we've gone off and drawn a sample of 809 people and observed a sample percent of 0.266. What we need to do is evaluate the area in this tail, then we'll double it. All right, so let's go find the area in this tail. So what is the probability of observing a p greater than 0.5266? Well, it's going to be approximately equal, using the CLT, of us observing a z greater than 0.5266 minus the mean, divide by the standard deviation of this distribution. Now at this point, we have a small decision to make that doesn't really matter. Here we've got two possibilities. So we could find the standard deviation of that distribution. The standard deviation of that distribution is sigma sub p. What's the formula for sigma sub p? Well, it's pi times 1 minus pi over n. Now, ordinarily, we wouldn't be able to find sigma sub p because we don't know pi. But in this case, since we've assumed that h naught is true, we've assumed the value of sigma sub p. So, therefore, why not use it? 0.5 times 1 minus 0.5 divide by 809. That's an 809. And if you do the math, this is equal to 0.01758, keeping 4 accurate digits. So therefore, let's go drop that in, 0.01758 this is equal to 1.51. And the answer is 0.065 or so. The p-value then is 2 times this, which is equal to 0.1306 if you work out more accurate digits. So this is greater than 5%, so we cannot reject H naught. Our conclusion is the race is too close to call. At least with the sample. So let's go over exactly what that 13% tells us. 13% tells us that if the race were perfectly tied, there's about a 13% chance that we'd draw a sample of 809 people, giving us a test statistic that's this extreme or more extreme in either direction from it. And 13% is pretty common. So we cannot rule out 5%. We can't rule out the possibility that we're tied, or even worse yet, a smidgen behind. So that's one way to do this problem. Let me now show you another approach. So the other approach is to use confidence intervals. Let's find the confidence interval. Now with a confidence interval, we don't assume the null hypothesis is true. Instead, what we do is we go out 2 standard errors. What's the standard error? So the standard error is S sub p. S sub p is equal to p times 1 minus p over n. So this is going to be 0.5266 instead of 0.5, and then 1 minus 0.5266 all over 809. Now there's not much of a difference. This is equal to 0.01755, keeping 4 accurate digits, so there's not much of a difference between that number and that number. But if we want to be right, we should be using the standard error to find a confidence interval. So the confidence interval is going to be 0.5266 plus or minus 1.96 times the standard error, so 0.01755. And if you expand this, you get the interval 0.4922 through 0.5610. So this gives us a little window where we think the true percentage of people voting for our candidate falls. Now to do a hypothesis test with this, what we're going to do is take the reference value. So the reference value is that thing up here in the null hypothesis. And note that that reference value is contained in the confidence interval, so we cannot reject 0.5 as a possible percent in this case. So our conclusion is the same. The race is too close to call.